the second lecture on diffusion equation, solution of diffusion equation. In the earlier class, we have solved the one-dimensional diffusion equation as applicable to a straight rod lying along x-axis and solved the equation subjected to different boundary conditions. The last case that we consider, that is the case boundary condition type 4 that we discussed, was that the u at x0 t is 0 while u at lt was theta l. That case we considered and solved the problem. Another way of treating this is that we consider the diffusion equation del 2 u of xt del x2 is equal to 1 upon sigma del u of xt dt, and as per separation of variable technique we write x of x and t of t, which we get 1 upon x d2x dx2 is equal to 1 upon sigma square t dt dt. Now this is the separation constant. If we choose separation constant to be 0, then this solution, this is the separation constant, we choose to be minus k square. Then we got the solution as u of xt we obtained as a sin kx plus b cos kx times e to the power minus sigma k whole square t. This is the solution for case separation constant minus k square. If we could take separation constant to be 0, then the solution will be u0 x of t is some a0 x plus b0, and there is no time part. In that case, we can choose the solution. The most general solution is u of xt to be a0 x plus b0 plus this part a sin kx plus b cos kx as the solution, and we can apply the boundary condition directly on it to get the same result that we have obtained in the last class. Now we consider another category of problem. This is the type 5 boundary condition, when there is a heat exchange is allowed at one end of the rod. So the type 5 boundary condition, one end is at a fixed temperature, we call it u of xt, it is at a constant temperature, and heat exchange is allowed on the other end. The heat exchange may take place in two ways. One is by conduction. The rate of conduction is determined by del u del x, and if u be the excess temperature over the surrounding, then rate of radiation exchange depends on u, the temperature difference, assuming Newton's law of cooling to be valid. If we assume that the rate of loss due to one process is exactly compensated by the rate of gain by the other process, by these two processes are conduction and radiation, then the condition is that h u at lt is equal to del u del x at x is equal to L is equal to 0. These are the two boundary conditions. Now we know that the solution u solution is u of xt is equal to A sin kx, b cos kx, and del u del x is equal to k a cos kx minus b sin kx. If we apply the boundary condition, this condition sets b is equal to 0. So we have this reduces to a sin kx, and this as b is 0, this becomes ka cos kx. Now we apply the boundary condition, this boundary condition, that is h times a sin kl, h times a sin kl plus ka cos kl is equal to 0, or we define tan kl is equal to sin kl by cos kl is equal to minus k by h. We define it minus kl by hl, or we write this is tan of beta, this is kl, tan of beta is equal to minus beta upon kl, where beta is kl and is dimensionless quantity, because the dimension of k is 1 upon l, is that of 1 upon l. This is a transcendental equation. So to solve this, we set y1 is equal to tan beta and y2 is equal to minus beta upon hl, and we draw both the graphs on the same graph paper, and the point of intersection gives us the solution. As for example, if we plot, this is beta and along this is yl, then starting from 0 at beta is equal to 0, tan beta is 0 and it goes to infinity at pi by 2. So this is the value at pi by 2. This is the value 3 pi by 2, and this is pi. So tan function is like this. This is 3 by 2 pi, and then we have this is 5 by 2 pi, and this is pi, this is 2 pi. And this is the y1 graphs in different sections. These are the plots of y1, and y2 is a graph. This is y2, which is a straight line with negative slope. So this is the first intersection that in this region from 0 to pi by 2 there is no intersection between the graphs, because y1 is essentially positive. Starting from 0 it goes to plus infinity, so there could not be any intersection. In the region from pi by 2 to pi, y1 is negative, so there is an intersection in this range. So this gives you the smallest value of beta 1. Then another intersection takes place between 3 pi by 2 to pi. This is beta 2. This is beta 2. We see as we go towards the higher values of beta, the intersection point beta shifts towards the 2n plus 1 pi by 2 towards us. Here we see also that the k values are discrete, but in either other cases we got k values either as k is equal to 2n pi by 2l, or it was 2n plus 1 pi by 2l. We got it from the value sin kl is equal to 0, and this was from cos kl is equal to 0. Here we get similar values, that is discrete values of k, but they are not as simple as this, but we are to extract this through numerical solutions. One way of solving, we have shown the graphical method of solving this problem. Otherwise, one can use the numerical techniques, that is the bisection method or Newton-Raphson method for the solution of this equation. So we have solved the one-dimensional diffusion equation as applicable to a straight rod lying along x-axis, and which satisfies 5 different categories of boundary conditions. The boundary condition that we considered is this. We summarize the different boundary condition that I have considered is that we solve del 2u of xt del x2 is equal to 1 upon sigma del u del t with the solution, and the boundary condition was that u of 0t is equal to u of lt is equal to 0. This is one type of boundary condition. We say that both the ends are at the same temperature. Then second boundary condition was del u del x at x is equal to 0 is equal to del u del x at x is equal to L. This was we call insulated ends. Insulated ends. Then we applied that one end is at a fixed temperature and other end is insulated. This is one end insulated. One end is insulated. Fourthly, we consider another type of case, that is u of 0t is equal to 0 and u of lt is equal to theta L. Then we, in particular case, k is equal to 0, when the separation constant is 0, that solution has to be taken into consideration. And finally, we solve when there is a heat exchange allowed at one end and 0t is equal to 0, and another thing is h u of lt plus del u del x at x is equal to L is equal to 0. Heat exchange at one end. At one end. These were the 5 conditions, different boundary conditions that I have considered in solving the diffusion equation in 1D Cartesian system. Now we shall continue our discussion on one-dimensional diffusion equation, but this time we shall consider curvilinear coordinate system. So 1D diffusion equation in curvilinear coordinates. To be specific, we shall consider the transient state of heat flow in a cylindrical and having spherical and cylindrical symmetry. So our discussion is 1D diffusion equation in curvilinear coordinates. Curvilinear coordinates. First is spherically symmetric case. transient state of heat flow in a spherically symmetric case. You know that the general Curvilinear diffusion equation was nabla square u of RT is equal to 1 upon sigma square del u of RT del T. This is the general equation. In spherical symmetric cases, this nabla operator becomes 1 by R square del R of R square del R. This operates on u of RT is equal to 1 upon sigma square del T of u of RT. Here we have considered spherically symmetric case, so the temperature function depends only on radial distance r and on temperature T and on time T, time T. So as per separation of variable techniques, we assume r of T. This is r of r and T of T. We use this, and for non-trivial solution we get r square r ddr of r square dr is equal to 1 upon sigma square T dt, and we use the separation constant to be minus k square, so that T equation becomes ddt is equal to minus sigma k whole square T with solution T of T is of the form e to the power minus sigma k square T. This decreases exponentially with time, and the R equation becomes ddr of r square dr plus k square r is equal to 0, or we have r square d2r dr2 plus 2r dr plus k square r is equal to 0. This is basically Helmholtz equation in spherically symmetric cases. We can solve this equation, we opt the procedure that we have used in connection with spherical waves. So we write r of r is equal to r to the power n w of r, and we can use this substitution in this differential equation, so that r prime is equal to r prime is equal to r to the power n omega prime plus n r to the power n minus 1 omega, and r double prime is equal to r to the power n omega double prime plus twice n r to the power n minus 1 omega plus n into n minus 1 r to the power n minus 2 omega. When we substitute this all these things in the radial equation, we see that this is r to the power n plus 2 omega double prime plus twice n r to the power n plus 1 omega prime plus n into n minus 1 r to the power n omega. This term originates from the first term. From the second term we get 2r to be multiplied, so 2 r to the power n plus 1 omega prime plus 2n r to the power n omega plus k square r to the power n plus 2 omega is equal to 0, or r to the power n plus 2 omega double prime plus, if we can and we have this term is n into n plus 1 r to the power n plus k square r to the power n plus 2 omega is equal to 0. We set n in such a way that the coefficient of first derivative term is 0, that is n is equal to minus 1. Then this term is also not there, will not be there, and the resulting equation will be omega double prime plus k square omega is equal to 0 with solution omega of r a sin kr plus b cos kr, and the r equation will be r of r will be 1 by r. This is, as n is 1, this is minus 1, this is omega r by r, so this is 1 upon r a sin kr plus b cos kr as the solution of the radial part. So the total solution, which comprises of r and t, so u of rt is equal to 1 upon r a sin kr b cos kr e to the power minus sigma k square t. Now to move further, we need to know the boundary condition, and if we apply the specific boundary condition, then some simplification can be obtained. Say for example, if we said that a sphere, we have a sphere of radius r and u a sphere of radius a and u of at is equal to 0, then we find immediately that b is equal to 0. So sorry, if we put r this, if we put u at at is equal to 0, firstly you at r is equal to 0, the solution has to be finite. At r is equal to 0, this part is 0 and this is b by r, at r is, so b by 0 form. So for the function to be, the solution to be finite at the origin, b has to be 0, in which case the solution reduces to 1 upon r, a by r sin kr by r e to the power minus sigma k whole square times t. This solution is finite at r is equal to 0 because it is a k times this part will be the solution at r is equal to 0. And if we say that the solution is 0 on the surface of a sphere of radius a, then we get a quantized value. If we say that u at at is equal to 0, this gives us that sine of ka is equal to 0, that is k is equal to n pi by a. So the discrete values of k are enters from this, and since this all values of n we get solution, and the most general solution will be a superposition of states. So for a particular value, first thing is that u of 0t is equal to finite, which allows that b is equal to 0. Then we write u of at is equal to 0. This says that k n is equal to n pi by a. So we get specific solution for n un of rt. Un of rt is this part, a by r sine of knr e to the power minus sigma kn square t, where kn is n pi by a, and the most general solution is the superposition of all these solutions. So the general solution u of rt is summation over n is equal to 1 to infinity un of rt. Writing explicitly, this becomes n is equal to 1 to infinity n by r, sorry, there n by r sine of knr e to the power minus sigma kn square t. The initial condition is supplied as u 0 r is equal to u at r0. This is equal to summation over n is equal to 1 to infinity an r sine of kn, that is n pi r by a, and we can get a n from this solution. Now we derive this equation as u0 r times r is equal to summation over an sine of n pi r a, and if we multiply it by sine of m pi r by a and integrate between 0 to a, we get a m is equal to 2 by a integration 0 to a u0 r times r sine of m pi r a dr. This is the expression for the expansion coefficient. Another type of flow is the cylindrical heat flow. In that case, we solve diffusion equation in cylindrical coordinate system, and due to cylindrical symmetry only rho part will be there. So for cylindrically symmetric case, heat flow. Here the diffusion equation reads as 1 by rho del del rho of rho del del rho. This is the nabla part operating on u of rho t is equal to 1 upon sigma square del u of rho t del t. So because the situation is cylindrically symmetric, in cylindrical coordinate system rho phi z, we have only retained the rho part, and the solution u of rho t is written as h of rho t of t, and when we substitute this for non-trivial solution, this is h dd rho dh d rho is equal to 1 upon sigma square t, and the separation constant is k square. Obviously the t solution as we obtained is e to the power minus sigma k square t, and this part, this rho equation becomes dd rho of rho dh d rho plus k square rho h is equal to 0 or this is rho d2h d rho 2 plus dh d rho plus k square rho h is equal to 0. Earlier we have solved in connection with a cylindrical wave. We solved this equation by setting h of rho is equal to rho to the power n w of rho, and we assumed n in such a way that the coefficient of w prime becomes 0, which gives 2n plus 1 is equal to 0, that is n is equal to minus half, and we arrived at a situation that the w double prime plus k square plus 1 upon 4 rho square w is equal to 0. If we could neglect this part, then w has a sinusoidal solution, and we are good from that. The h of rho approximately behaves as a sin k rho plus b cos k rho upon root rho. Note that in the case of wave equation, we assume the solution to be e to the power plus I k rho, and for heat conduction we are assuming the solution in the form of stationary waves. But we shall describe another alternative method for solving this equation. We multiply both all alone by rho, so we get rho square d2h d rho 2 plus rho dh d rho plus k square rho square h is equal to 0. We compare this equation with x square d2y dx2 plus x dy dx plus k square x square minus nu square y is equal to 0. The solution of this equation was j nu of kx, some constant a nu of, and plus b nu of y nu of kx, where these are the Bessel function of first and second kind. Comparing this, we see that these are given by the solution nu is 0, so h of rho is given by a j0 of k rho plus b y0 of k rho. But if we conclude that rho is equal to 0 is within our region of interest, why all the Neumann function diverges at the origin, so we said this is 0 and the equation becomes a j0 of k rho. And if we consider very high values of rho, then this is rho tends to infinity, then this is a sin k rho plus b k cos rho by root rho. This is the asymptotic behavior of Bessel function. So we come to the same solution either through substitution or directly through Bessel function. So the solution becomes one is this part, another one is the temporal part. So the solution becomes u of rho t is h. This was with h, where h is some constant, the a j0 k rho e to the power minus sigma k square t is the solution. Now if we say that the solution is we have a situation that u at at is equal to 0, u at at is equal to 0, then this means that J0 of Ka is equal to 0, which is equal to J0 of lambda 0 m, where lambda 0 m is the mth 0 of J0. So we see that Km is equal to lambda 0 m by a, and the discrete values of k are obtained obtained from the zeros of Bessel functions. And we, in that case, we can say that the general solution is so a particular solution is um of rho t is equal to am J0 for k is now km, so we write this with for this is lambda 0 m rho by a, this is the value of km, and e to the power minus sigma km square t as the solution for a given m, and the most general solution is rho of t is summation over m is equal to 1 to infinity of rho t. And on substituting this value we get the general solution. Now we can impose the initial condition, let me write it. This is m is equal to 1 to infinity, because there are infinite number of zeros. So this is J0 e to the power minus rho km square t is the general solution. Now the initial condition is u0 of rho is equal to u of rho 0. This is equal to summation over m J0 sum over m. This is the initial condition. Now if we want to find out am, then we are to apply the orthogonality relation of Bessel function. So to this end we multiply it both the sides, that is u0 rho multiplied by rho J0 lambda 0 n rho by a, and integrate it from 0 to a over d rho. This is the left hand side, and on the right hand side we have summation over m am, and then rho J0 n rho a d rho integrated from 0 to a. The result is a square by 2 j of 1 square lambda 0 m times delta mn. And For n, this gives you a n a square by 2 j1 square lambda 0 of n. You see that these lambda 0 n are the zeros of Bessel functions of j0, but they are not the zeros of j1, so this value is non-zero, and which enables us for the determination of the constant an. That's all about the diffusion equation in 1D. We have applied diffusion equation for linear alone in one-dimensional Cartesian system. Then we have solved the transient state of heat flow for spherically symmetric and cylindrically symmetric cases. In the next class, we shall consider the diffusion equation in 2D.